Hello friends, very good evening and welcome back. So today it's time to know how to predict for numerical data. So when we were discussing the last few sessions, it was like the classification model building, which is a part of supervised learning algorithm. So supervised is divided into classification and regression. Classification and regression. Here it is non-numeric, numeric. Okay, so when do you apply regression model building? It is that when you want to predict any numerical value, then you have to apply linear regression. So what is this regression all about, and what is this very, very important here for us to understand the concept of this? So friends, we have understood that y is something, right? And which is nothing but we take into consideration something called as base equation. Okay, and this base equation is very, very important when you are building regression models, because here x is called as independent variable and y is called as dependent variable. Okay, so whatever might be the x, y is always dependent on this. So when you want to predict y, you want x. So x can be anything, whatever you feel, you can pick. Right? Like tenure, monthly charges, how many days he was with us, he own internet service, right? Does he own on mobile data also? Right? TV is also along with that. You have it or not, but you predict your y, which is numeric. So y is always called as, in the terminology basis, you call it as y being an dependent variable and x being your independent variable. Okay, so whenever you want to build a regression model, suppose I have tenure and the monthly charges. Okay, when you have monthly charges and you have tenure, right? So if these two are having very, very good relationship, the plot which will help us to find out the relationship between both of them is called as a scatter plot. Okay, the plot is called as a scatter plot, and then this plot will give you the relationship whether both are linear or not. They are moving in the same direction, is it positive direction or negative direction, and how strong is the relationship between them, just given by the strength. So tenure is something which is very, very important for predicting monthly charges they are spending, or you want other inputs also. Here we are not aware of it, but here it's very, very important what inputs you pick for prediction of y. That is very, very important. So to build a regression model here, what is that we are doing? We want to do a scatter plot. Assume that if a person is spending, he's with us for 4 years. A person is with us for 4 years. Okay, then what is that I'm going to do? Is that I want to predict, right, how much amount he's going to spend. Okay, what will be his monthly charges with my network. So I have tenure and monthly charges for various people's data. Maybe 1,000 people's data I have. Okay, so what should I do now? I have to estimate for a person whose tenure is 5 years, and what can be his monthly charge. and how much he's going to spend with me. Okay, he liked the services or he did not like the service. Did he churn in between? He came back, right? What are the services he's having? How many connections? How many people are using the same network, right? All these things you take into consideration and you have to predict for 4 years or 5 years, guys. So you got a scatter plot here, and this scatter plot, you draw one line here where the maximum data points will fall on the line. If at all I want to estimate, I cannot do it randomly. What will I do? I'll map onto this. Wherever it is intersecting this line, I say that this is my y hat value. If a person is spending with us, the tenure is 5 years, his monthly charge is this much. It is a y hat. So when I plot this, if the relationship happens to be a linear relationship, right? It is going to be a linear relationship like this. It should be a straight line, and you check the intersection of the point and you get the predicted value. When you're checking this one. So y is nothing but a predicted value for a given input. For a given input. Okay, this concept is called as regression. Okay, this concept is called as regression. How do you find out? The data is scattered and you got many lines here. Which line makes more sense here? So you have to choose a line which is the best fit line. Okay, you have to choose a line which is a best fit line. Okay, so when you are doing this regression model is built for unknown data and you want the best fit line. So that's where we go for a technique which is called as Ols technique. You have to choose a line in such a way that that line would give you maximum data points will fall on the line and will give you the best prediction. That line can be anything like this, anything like this, anything like this. Line can be anything. If we want the line which will capture maximum information. So that's why we are considering this as y is equal to mx plus c, which is your equation of a straight line. That you will map to regression equation and you call it as beta 1 x1. You should draw a line which captures as much information as possible. The maximum number of data points have to be covered, but there is a chance that you are ignoring few data points. So you should draw a line which can capture as much as information you want. So what is this ordinary least squares you are getting? Ordinary least squares is nothing but you are predicting this one, but original value is this. This is the error term. This is the error term. So this is equal to y is equal to mx plus c, where c is equal to your beta naught and m is equal to beta 1, which talks about the slope. Just talking about the slope. Y is c is a constant here, right? These are your slope. Beta naught is this one. For this, you are adding this error, which is this deviation. The beta 1 is your slope here. The data point you are estimating should fall on this line for any given value of x, and whatever I'm trying to predict here would fall on the line. So if at all I calculate all these deviations, right, how much it got deviated like this, how much you are estimating should fall on the line and you're getting deviated. There is nothing but your error term. And this, if you take all these errors, y minus y hat whole square, right? If you add them, add all the errors, right? And you get that sum of the square errors should be least. Sum of the square errors should be least. So this is what we are going to do here. But what if you have more number of variables. If at all you have single, only one, right, like this. If it is single and continuous, you go for simple linear regression. If you have x1, x2, x3, you call it as multiple linear regression. Okay, so multiple linear regression means more number of data points. If at all you have any values which are discrete, right? You have for something like gender column, something like that, you can convert it into a discrete by using dummy variables. By using here dummy variables. So this is what we can see here. So what are the other things you need to understand? It is nothing but now this is a equation of your straight line, right? And to find out the relationship between two, whether your input and output are having some relationship or not, there is a metric which is called as correlation coefficient. There's a metric which is called as correlation coefficient. What is this? It is given by small r. Its value is -1 to +1 and r should be greater than 0.85. Means your y and x are having very good correlation. You can move forward, go and build the model. Okay, but what we will do is we will take more data here. That data should hold good for us. So I'm using pandas as PD. So more things to understand when you are studying this hands-on. I'm using a data set. Okay, this is the data. Hopefully it should be there. Okay. So I have, okay, I'll show you here. Right? If I take only tenure and I take only monthly charges here, so if these two are having very good relationship or not, is there no really important for me prediction of monthly charge? For every customer, their tenure, their charges, tenure, charges. The person with a more number is loyal to us, right? Is his monthly charge, right? So when we are talking about the data set here, I may have multiple variables here, right? I have to do a kind of feature engineering on top of this to understand whether this is really good to go with all these data points or not. All these, sorry, not data points, columns or not. So order, customer ID, this is the interaction, whatever happened, which is a city, okay, which state, which country, its zip code, right? What is the population in that particular city? What is the area? It is urban area or suburban area or rural area. Then what is the time zone there? What is the job of that particular person? He is an environmental health practitioner or programmer or multimedia chief financial officer. Okay, and this is how many children they have. That is also important or not, we don't know, but they have given. If more number of children are there, more usage of internet can happen. What is the age of that particular person? What is the education he has done? What kind of job he does? What is his income? Whether she is married or not? What is his gender? Okay, churn. Okay, and outage per week. Okay, emails. What are the contacts they have? Yearly equipment failure only one time. Any technical issues? What is the contract they have done? What is this? You have a modem or it is not modem? It is they are using a tablet phone. Okay, for internet services, a DSL or a fiber optic. They use phone also for multiple purpose. Are they giving any payment for online security? Are they giving anything for online backup? Are they paying us for anything for device protection? Tech support, whether it is a streaming TV, also movies also, whether it is a paperless bill, whether the payment is credit card or a bank transfer, There comes your tenure, monthly charge, bandwidth every year, how many devices they are using, friendly contacts, right? Number of screens they have, surveys completed, right? And with the what is the connect with the customer, how many spam emails sent, satisfaction scale, how much he is satisfied. Okay, so the chance is there that all these inputs are important or not, we don't know. We should understand, pick up them and do the analysis. So all this which is not required here, data.drop, city, country, zip code, job, customer ID, interaction, case order, I drop them. I even drop what is his employment, payment method, education, time zone, access is equal to 1. I drop even that. Okay, it's not required for us. So whatever the rest of the columns you have here, I have applied because it is categorical data, right? So it is, if you see here, yes or no, yes or no, yes or no. So dummy variables should be created. So I'm just converting them into lb.fit_transform. So now what is that I have done here? I have checked for any NA values, happen to be not there, and I've checked the histogram. All the continuous data, if you observe, it should be normally distributed. If they are not normally distributed, you have to make them normally distributed. How do you make them normally distributed? You have to go and apply some transformations to make the data normal. Okay, so maybe all these are not important for my analysis. I don't know, but I have to check them. Okay, if at all I have any duplicates, I check them. Okay, if you observe that all the data points will not fall in the same range here, all the numeric data, this is different, the charges are different, and you have tenure is different, bandwidth is different, right? All the numeric data, they're also different. I want to bring them to the same scale. So what am I doing? I'm doing min max scalar. I'm doing min max scalar and I have got the output. Like all the range will be 0 to 1. Then I take my data, I split it. I will split my data. So what it is going to do here, I will split my data and the metrics, like yesterday we have seen for classification, it is confusion matrix or cross tab, but here you have mean square error because your idea is only Ols technique, ordinary least squares, and you have to get the mean square error. So these are the columns what we had. Okay, so I'm taking stash model.formula.api here, smf.ols. This is my y column, tilde inputs. All the inputs I'm taking, just taking because the data is there with me and I'm fitting my model. Okay, this is the summary I have got. If you observe, the first thing you have to focus here is two things. All your p values. First thing you have to focus is your p values. It is nothing but what is the chance that whatever beta naught, beta 1 values you got here, right? Whatever beta naught and beta 1 values you got here, shall I move forward with them? Shall I use them for prediction or not? To check that, you are going for p value. Now, what is p value here? P value is nothing but the probability value, the chance of you going wrong. If p value, whatever you got is 0.0, you will compare it with alpha, which is nothing but we call it as significance level in stats. You say that it is the significance level, and in stats you say that if your p value is very, very high, right? So you have to go with, should not go with these values, these beta naught values. If p value is low, then only you have to consider these values. That is the interpretation of this, which is a concept of hypothesis testing. So the equation is beta naught plus beta 1x1 plus beta 2x2, so on and so forth. How would I write this equation now? y hat monthly charges is equal to intercept, it is 87.21 plus beta 1 minus 0.04 into area plus 0.047 into children plus I'll take 0010 into age plus income as 1.8 into 10 to the power of 8. It like that. These are my beta naught, beta 1, beta 2, beta 3, beta 4, beta 5, beta 6, 7, 8, 9, 10, 11. Whatever I have, all that I have taken. But if you see the corresponding p values, none of the values except very few, they are significant. Right? The second thing you have to check here, very important part here is your R square value. R square value is nothing but small r is your correlation coefficient, but if you check this is called as your coefficient of determination. Okay, it is called as coefficient of determination. What is this coefficient of determination? It is given by R square value. It is nothing but goodness of fit, how well your model is predicting. It is saying that out of 100 values you pass to me, 86 values I predict correctly. Out of 100, 86 values it predicts correctly. And then this F statistic value here, if this also should be less than alpha, which is 0.05, right? Phi is being your 5% of chance of you going wrong. 5% chance of you going wrong. This should not exceed this 5%. So if this exceeds this 0.05, these values, this overall model is not good to move forward. So the model I have built is my Ols technique and it is going to pick up the things. Okay. But if you try to find out the correlation coefficient between y, x1, x2, each input you take should be independent of each other. They should not have any dependency. You take x1 to x100 also, right? All the inputs should be independent. All the inputs should be independent. Okay, if these are independent, then only your model will give you good results. If there is some dependency here, right, you cannot move forward. That is something which is very important. But if you see here, all the values are not up to the mark here, and you got your R square value 0.58. It's okay. So if your R square value is 0.58, is greater than 0.8, it is a good model, is what people say. The standard we have maintained, this value will range from 0 to 1. Higher the R square, better is your model. But if you see here, all the features are the really important for prediction of monthly charges. He's going to spend, if he's spending so much and there is a chance that he's getting irated, he has registered so many complaints and he did not recharge for a couple of days. Right? He did not recharge from a couple of days, so there can be some mismatch that what happened here, all that. So what is it you are going to do? This is going to, this is really going to help us so that we can stop or we can give him some offer, and there's a chance that he may move away from our network. Right? So what is it we have to do here? We have to give the best predicted value. This value should be good, means that is your R square. But whatever inputs you are taking, all these inputs are good or bad, you don't know, we don't know. So you have to do a kind of feature engineering. But if you see here, This is beta 1, beta 2, beta 3, beta 4, and you have here beta 5, beta 6, right? Beta 7, beta 8, all these values you are taking such a big equation here. Definitely performance of your model is very, very slow. So there is something called as principle of parsimony. Okay, there is something which is called as principle of parsimony, which is definitely going to help you, which is nothing but a person, Occam's Razor. He has said that better the model only if the model is simpler. So the statement was, simpler the model, better is your model. So you have to do a lot of feature engineering to cut short which are the important, which are not important. Okay, that is your important point to remember here. So and my p-values are not significant here, right? And if you see here, there are few very, very huge data set here. All the people, students are sitting here. There is few things which are outstanding here. So maybe your p-values are which is corresponding to beta 1 or whatever betas it is corresponding. It is not working if they're not under the range, that is, it is greater than 0.05, it means that there might be few people's data, few customers' data, which is not allowing them, which are like a weird pattern, some kind of outlier, we can say. So if you see this graphics influence plot of your model, you can see that there are few data points which are not in sync with the other data points, right? So same also. So what am I going to do here? We have to take a call and delete few unwanted columns, and you have to build your model. To our surprise, we have deleted so many other, right? So what did I do? I have taken the model and I'm showing you the summary. So whatever are there, whose p-values are there, you have got all the p-values significant. And the good thing here is, if you add any input column, see here the same. So it's a good model only. Now what is this adjusted R square? What is this adjusted R square? R square and adjusted R square, there is a flip side flaw in R square. What are the flaws of R square? R square is nothing but if you add any input, if at all you are adding an input, it will, if you add an input, it will definitely will increase your R square. Right? So it will definitely increase your R square. Whether the added input is good or bad, we don't know. See here, we have added so many inputs, we have deleted so many inputs, still your R square value and this R square value are going hand in hand. It means that whatever inputs you have taken, they are good enough for your prediction. So these p-values are significant, and there are few p-values which are not significant, right? Maybe they are not important, that is also one point, right? Or else what we can do is we can remove these data points, two data points which are totally outstanding from the other, and build a model, create a new data set and build the model, right? So I got this model which is a final. I take this model and I'm doing predictions, right? These predictions should give us errors. This is what you are going to check. Are these predictions giving us errors? So the predicted value and your actual value, how do you predict? How do you get your calculations here done? Here the calculations are nothing but they are done using your RMSE. It's nothing but root mean square error. This root mean square error is nothing but take errors, okay, then square them, okay, you square them. After you do squaring, okay, after you do squaring, what is it you are going to get? This average you have to take, right? You have to take the average. So when we are taking this average, right, you are getting your, because you are squaring it, you got your errors square. That is nothing but units square. So this units square is something which is the wrong way of calculating error, so that they can root of it to get back it. So you call it as root mean square error. It is directly available here. So I'm taking receipts, right, from my model and I'm doing a QQ plot. So there is something which is called as line assumptions. Okay, there is something which is called as, we call it as line assumptions. So when you take this line assumptions, it is nothing but we are saying that your inputs, your beta naught, beta 1, beta 2 values should enter the linear regression line linearly. Okay, whatever you are getting, okay, they have to go and fit in this line linearly. That is linear. And we have to concentrate more on your errors. Here, errors should not have dependency. Okay, errors should not have any dependency. So what you are doing here, when you want to do this, when we are trying to do this, we have to check whether the errors are independent or they are dependent on each other. Okay, so what is going to happen here? If they have dependency, you call it as autocorrelation problem. You call it as autocorrelation problem. So this is something which you need to focus, and the errors should be normally distributed. Now, what is this normally distributed? For any data which you are working on, you should have, for any data you are working on, if it is a continuous in nature, right? If it is continuous in nature, you have to check for normality. Okay, you have to check for normality. Now, what is that normality? Normality is nothing but it is a Gaussian curve. It looks like this. If you do a QQ plot, right, it will have a straight line and data points should fall on the line. Okay. So what is that we will do now? We have to check for the errors are also being normally distributed or not. If the errors are not normally distributed, then your model happens to be not a good model. You have to keep an eye on it. Okay, so that is something which is very, very important. The other way around here is your errors should be in line like this. So when you check you got a straight line like this and you have a scatter like this. Okay, when you have a scatter like this and you have the line here. Okay, if the scatter is like this now, it got widened and it's like a V. Okay, so what will happen? You got this line. Suppose you are predicting this is your y hat, but if your y happens to be this, here if you see the error is very, very less. But someone with 4, someone with 11 years is loyal to us, or 11 months is loyal to us. If you see this error, if this is your actual value, this you say that this is your actual value, but actual value is this. This is your predicted value. This is your actual value. The error is more. Okay. So what is going to happen? This is not a good model. This problem is called as heteroskedasticity. Okay, so when you get to find out the relationship between this, you should have the data scattered should be there here in between the two parallel lines. It should be there in between two parallel lines. Okay, so it's very, very important that you have to check this and move forward. So QQ plot is something very, very important. Error should be normally distributed. Error should not have heteroskedasticity problem. Error should be independent, right? So all this will make our model a good model, checking all these values. And finally, if you have your inputs, right? This is nothing but these inputs should be not have any dependence. They should be independent of each other. The inputs should have no dependency among each other. So what is going to happen here? So when it is going to have dependency, that problem is called as co-linearity problem. So you have to check that also. How do you check that? You check your R, which is a correlation coefficient. Okay, which is called as correlation coefficient. This is going to help you to know whether the inputs, whatever you have taken, are they dependent or they are independent of each other. Okay, that is one thing you have to check. So we are checking here with respect to errors. Right, this is a line what I'm talking about, and most of the data points are falling on the line here. Most of the data points are falling on the line here. So I can move forward that my errors are this. And my errors are normally distributed or not, I have checked. But the errors are do you find any dependency between them? And you have to check, are there any influential plots here? Influential, this one, right? So I feel that this is a good model and I will split my data. So when I split my data, I'm splitting it to 78, 30% here, 70 and 30, and I'm going to take that model, fit my train data. Okay, I'm going to fit my train data. This also will give you a summary, and see here, all the p-values are significant. I can take this beta naught, beta 1, beta 2, beta 3, beta 4, beta 5, beta 6. I'm happy with this model if I get a very, very less error, provided all the assumptions also should hold good for us. Okay, all this also should hold good for us. Okay, so I got my p-values, I got my r-square, and if you see, my adjusted r-square is also 0.856. Right? So I'm taking the model, I'm predicting it, taking my test data. Okay, now what am I doing? Test underscore precedes. So I'm trying to calculate actual value minus predicted value. Okay, it is actual value minus predicted value. So NP dot square root of error square, which you got as 16 is your error. So very, very huge data sets we are using here, right? And finally, if you predict on train, then you have the right fit here, 16.44 on the train error, and this is my test error. So linear regression is something we have to do when y is numeric in nature. So what are the things you have to check here? You have to check the p values, and corresponding beta naught value should be accepted or not. You have to check for your line assumptions. Right? Randomly, you cannot take any input for your model building here. Randomly, you cannot take any input for your model building. So what is that you do here? You have to take thinking twice when you pick up your data. Right? We don't know whether all the inputs, whatever you have, they are helping you to build the model properly. So we are doing a kind of feature engineering. We want to delete few columns. That is the last option what you should do. Right? If your train accuracy and your test accuracy happen to be nearly equal, right? So I will say that it is a right fit. Okay, that will be okay, that will be a right fit. If it is not a right fit, then you call that particular problem as overfitting problem. This is called as overfitting problem. Okay, so you should be very, very, take it seriously when it is overfitting problem. If it is underfitting problem, suppose both are very, 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 very high. Your train accuracy and test accuracy are very, very high. So what you have to do at that point of time? Accuracies are high, no problem. But accuracies are low, it is underfitting problem. Right? But if your train accuracy and test accuracy, they are not at all matching. This is around very, very good, and your test accuracy happens to be not even reaching like more than 5% difference is there, then it is overfitting problem. So linear regression talks about R square. The new parameter here, this is very, very important, which is your coefficient of determination. So I have used so many input variables. It means that I have to check R square along with that adjusted R square, because there is some disadvantage with R square. If you add any input now, if R square is increasing, if adjusted R square also will be increased, or it is same. It could be same or it would increase. Then added input is more value. Added input is adding a value to your model. Otherwise, it keeps on increasing and your adjusted R square keeps on decreasing. Your added input is a blunder input. You need not go for it. That is the interpretation here. So mostly what you check is your p-value, which is a probability value. If you are here, we have ignored them, right? But what is, which is very, very important here is when you are considering this, what is the satisfaction scale and what you are going to do, see the type of payment method, right? If a person is not having so much of interest, there's a chance that did he churn any time? Not there. So outage per week. So few people you can take this also, right? But there are few nominal data here which can be ignored, right? Because zip code, state, customer ID, interaction, state, column, country, column, zip code, right? So this is again, I think it's important or not, we don't know. We can keep it and we can remove it. But if the area is urban and this is not required again, what is the type of job he does? If he's an applications developer, right, and he lives in an urban area, and the payments he does is very, very high, and the tenure he might be there, but he's retired, he's a married, so she, it's a female, there's a chance that they may churn because they did not pay bill. Maybe more number of complaints are there which you did not attend, right? It's like month to month they did not like it, so that's why they went for churning. The internet service they are using is DLS. So this is how the pattern is being learned. So I might take so many inputs, I might take only 1 or 2 inputs to do this. So if you have more number of inputs now, is there any dependency between them? We don't know. If there is no dependency, well and good. If they have dependency, whether she's gender can be removed, right? Income is very, very important. Employment is important. If he's doing a part-time, but if his income is good enough, he's going to pay how much amount you are going to charge, right? How much you want to charge here. So this is how you have to start doing predictions using your why, right? So why is first you build multiple models. The second thing what you can do is instead of ignoring them, you can add few inputs which you feel were very, very important, right? You can add few things which are very, very important. Now you have to go and understand deep dive now why marital status is not important, whether he is married or widowed or whether divorced. That doesn't help in predicting what is a monthly charge, is what it might be. That's why it is 0.893, very, very high. If you see none of the values here, phone, tablet, modem, contract, techie, right? And these are the few inputs which you feel that these are the inputs which we feel that they are important, they are not important. Okay, so this is how we are building linear regression model. Okay, so what are the things we have discussed here? Y should be numeric. Okay, check whether your inputs are valid or not. It is nothing but they should not have any relationship. They should not have any collinearity problem. Okay, these should be independent of each other. Right, and then when y is equal to numeric continuous, right, you are applying linear regression. When you apply simple linear regression, you have only one input. If you have multiple inputs, you call it as multiple linear regression. Right? If you're having multiple inputs, they should not have any collinearity problem, and it should satisfy your line assumptions. So you should get sum of the squared errors equal to least. It cannot be 0, but it should be least. Means you have to get the best fit line. That best fit line here is nothing but your equation of a straight line. So the points to be focused is r square, adjusted r square, which is a goodness of it. To penalize the effect of r square, we are going for adjusted r square. So I don't know whether this is important or not important, but these p values are significant enough because I got a very, very quick equation here. Right, I have very, very big equation here. So to cut short it, so if at all you have collinearity problem, suppose you understand that few of the columns are not in sync here. Right, see, this is a categorical column, this is a categorical column, area, number, emails, number. See, this is your continuous. That is your continuous. Right, what else is continuous we have here? Satisfaction scale is number, discrete, right? Number of devices 0 or 1, streaming TV yes or 1, right? State not required, right? What is that you want? So this is helping you to find out whether how is the spread of the data, right? How is a division of your data? So you can do this label encoding, or you can get the dummies and check also. If you do dummies and check how many areas we have, the what you call it as state column, that many dummies you get very, very huge data set. So it becomes very, very difficult for us. So when you have more number of columns, and in that columns most of them are categorical, and that categorical is having so many number of variants, label encoding is the best approach. Otherwise one hot encoding will hold good, right? So these are the important inputs is what we took, and we have built the model. Right, this is the equation I have. So when I write this equation, this is how it looks like. Y hat is equal to 87 plus 0.79 into outsec per week minus 3.9 into internet service plus 32 into multiple plus 3.2 into online security plus 22 into online backup plus 12 into device protection plus tech support is equal to 56829 Okay, yeah, okay, no problem. It is 42.3 into streaming TV less 52 into streaming movies plus 0.09 into tenure minus 0.0013 into bandwidth. You take each and every data point from this, substitute these values, okay, from here, children, age, education, all these values, yes or no, you substitute it and you get to see, if you calculate, you get a value, that is your y hat value. Okay, that is your y hat value. Y is something which is already there, you are predicting. So this is what linear regression does. That's why these values are very, very important for us, which are given by. So these are called as coefficients or estimates, or you call them as the parameters, which are very, very important to get the best fit line. So this is linear regression, friends, and thank you all for joining in. Thank you.